This is Dr. D. Govardhan, Professor Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today the topic is shear force and bending moment diagrams for the cantilever beam subjected to point loads and uniformly distributed load. Here the figure shows the cantilever beam. Here cantilever beam is the beam which is fixed at one end, other end is free, and it is also kept in horizontal. Here there is cantilever beam AB of length as shown in figure is subjected to point load, the W, at free end B as shown in figure. The shear force at any section of the beam, here the shear force means the unbalanced vertical force which is acting on the beam is treated as shear force. So when I am considering a section at a distance of x from the point B, the unbalanced force toward the left side, toward the right side, with respect to the x point is equal to W now. But here, this shear force is treated as here negative. Why? Because the resultant of this force always tends to slide the beam in downward directions by keeping the left-hand proportions upward now. Hence, according to the sign conventions, it is treated as here positive force now. So the shear force here is acting positive force, and when it is moving toward the that fixed end A, the unbalanced force W remains constant and it is a W as shown in figure. Hence, while drawing the shear force diagram, draw length AB, which is equal to the length of the beam now, and at B, erect a line vertically upward directions to represent the point load W according to the suitable scoring. Since the shear force is a constant as we are moving toward the point A, that is the length of the beam, hence draw a line just parallel to AB to meet the vertical lines which is drawn at A position. This diagram is treated as a shear force diagram for the cantilever. Now the bending moment at B is equal to, which is equal to force into distance is required now. That means the shear force at B is equal to W into, since the 0, we are taking the reference from the right hand side now, and so W into 0 is equal to 0 now. It is represented at B is equal to 0. As we are considering the section of the beam at a distance of x, the bending moment is equal to W into x. That is, it depends upon the distance between the reference point to the point at which the load is acting. Hence, it is proportional to the distance. The bending moment at a point A is equal to W into x at x position. Similarly, at a distance of A, the bending moment is equal to W into L, where x is equal to L distance. But it is a nil vary now, that is proportional to the x now. Hence, the bending moment at A is equal to W into L, at B is equal to 0. So, at A, just represent the bending moment as a vertical line in downward directions to represent the bending moment as per the suitable scale. Join B and C by straight lines. This diagram is representing the bending moment. Here it is a negative bending moment because the effect of the bending moment is sagging. Now, based on point load which is acting on cantilever beam, we are taking one problem here. Draw the shear force and bend moment diagram for a cantilever beam of span 1.5 meters. Carrying point load W1 is equal to 1.5 kilonewtons as shown in figure 3A now. So the given data here now, the length of the span is equal to 1.5 meters and the point load is equal to W1 is equal to 1.5 kilonewtons acting at a B as shown in figure now. Now first we are drawing the shear force diagram which is represented here now, figure number B now. Okay, starting from point B now, already we discussed earlier, the shear force which is acting on cantilever beam is treated as positive. Here at B is to draw a line vertical and upward directions such that to represent a load of 1.5 kilonewtons now according to the suitable scale. That is here now 1 centimeter is representing 1.5 kilonewtons, that is 15 mm you have to take it now. As we are moving from B to X position now, the unbalanced force toward the right hand side of the beam remains constant, that is W. Hence the shear force is constant at X position also now. Hence draw horizontal lines up to X positions. Similarly, as we are moving toward the point A now, the unbalanced force which is acting on the beam toward the right side remains constant, which is equal to 1.5 kilonewtons. Hence, extend this horizontal lines up to just to meet the A point. So, this diagram is representing shear force diagram for the cantilever beam. The bending moment diagrams at B is equal to bending moment at B is equal to moment is equal to it is the product of force and the distance between the point of application to the reference point. Here that is equal to here now. Assume it is x is equal to 0 at B position. Hence at B is equal to the bending moment is 0 now. So again at a distance of x from point B position, the bending moment is equal to W into x. It is treated as a negative because of hiking effect. But here, at a distance of x, bending moment W into x, that means it is linearly varying with respect to the x or proportional to the x. Hence, it should be a straight line representing 0 to W into x. Similarly, at a point A, the bending moment is equal to force into distance, that is W into length of the span now, W into L, that is 1.5 into 1.5, that is equal to 2.25 kilonewtons meter now. So, by selecting suitable scale, join B with the 2.25 kilonewtons which is represented as per the scale by using the straight lines. This diagram is representing the bending moment diagram of cantilever beam when it is subject to the point load at free end as shown in figure. Similarly, draw the shear force and bending moment diagram for the cantilever beam of 1.5 meters carrying point load as shown in figure now. Two loads are acting now. Here one is acting at this position now. The second one is one more at this position now. So here the given data is length of the span is equal to 1.5 meters. The point load at B is equal to, the B point, it is equal to 1.5 kilonewtons. Here it is equal to 1.5 kilonewtons. And the point load at C is equal to, this is the point C, it is equal to 2 kilonewtons. Now, in order to draw the shear force diagram for this beam, first of all, draw the beam diagram now. Now, draw vertical lines in downward directions from the various points like this, and one more at the position and so on. Take suitable gap between this beam as well as the shear force diagram, a horizontal lines, which is representing the length of the beam now. At B, the shear force is equal to, that is unbalanced force is equal to 1.5 kilonewtons. So better to take one scale such that 1.5 kilonewtons is representing this 15 mm length now. That is take 15 mm upward directions. That is to represent the shear force diagram at B position now. At C position now, when I before reaching this point C now, the shear force, that is unbalanced force between B and C is the remains constant, which is equal to 1.5 kilonewtons. Hence, draw straight lines, that is horizontal lines, up to C position now. At C positions, again 2 kilonewtons that that is also a positive force. Hence, 1.5 and 2, that is equal to 3.5 is treated as a shear force at a point C now. Hence, this represent, that is 15 mm plus 20 mm, that is 35 mm to represent the shear force at a point C now. At A, the unbalanced force is again 1.5 and 2, hence draw the lines parallel to the length of the beam to reach the point A positions. So this diagram is treated as a shear force diagram for the cantilever beam when it is subjected to two loads 1.5 kilonewtons and 2 kilonewtons as shown in figure. The second one is a bending moment diagram. Again draw the lines since it is a negative bending moment diagram for the cantilever beam. Draw horizontal lines. At B, that is a free end, the bending moment is 0. And at C position now, the bending moment is equal to force into distance, that is 1.5 into 0.5, which is equal to 0.75 kilonewtons meter now. The bending moment at A is equal to, these two forces are acting towards the right side. One is 1.5 kilonewtons, one more is 2 kilonewtons, hence it is equal to 1.5 into 1.5. Here the length of the beam is equal to 1.5. Load is acting 1.5, hence it is equal to 2.25. That is bending moment created by the load 1.5 at A position is equal to 1.5 into 1.5. Again, the second load 2 kilonewton is there now. It is equal to 2 into, again the load is equal to here 1, because the length of the beam is given 1.5. Already 0.5 is over. The remaining length is only, it is equal to 1 now. That is 1 into 2 now. So totally it becomes 1.5, 1.5, 2.25 plus 2, which is equal to 4.25 now. So just represent 4.25 according to the scale, which is acting downward directions, and join these points. One is up to C, one straight line. The second one is one more straight line. This is known as shear force bending moment diagram for the cantilever beam. Okay, problem number 3. Draw the shear force and bending moment diagram for the cantilever beam as shown in figure now. So here the length of the beam is given, the given data, the length of the beam, it is equal to 2 meters is given now. AD, this is the total length of the beam is equal to 2 meters. But from D position now, at D 800 newtons force is acting downward directions. At C, that means from 0.8 meters from the D position, a load of again 500 newtons is acting downward directions. Again at B, that is from 0.7 meters from C, again 300 newtons is acting downward directions. We have to draw the shear force diagram for this beam when it is subjected to 3 types of forces as shown in figure now. So first of all, identify the shear forces at various cross sections of the beam. The shear force at D is equal to, generally we are calling here FD, which is equal to 800 newtons now. Or simply just with respect to the point, if the forces which are acting downward directions on the beam, that shear force, that forces are treated as positive now. So here 800 is a positive. So at D position now, between D and C, there is no force is acting now. Hence, the shear force is a constant between E and F as shown in figure in 2 here now. But at C, the shear force is equal, total shear force is equal to 800 plus 500. Hence, here you have to raise in upward direction to represent additional force of 500 newtons now. Or in other words, the shear force at C is equal to 800 plus 500, which is equal to 1300 newtons. The shear force at B is equal to, at B, because there is no force is acting between B and C. So the shear force which is there at C position, it is also remains constant up to B position. Hence, it is the horizontal line now. At B position now, the total shear force is equal to 800 plus 500 plus 300, which is equal to 1600. That is additionally 300 force in nothing but upward directions. Again, there is no force between A and B. Again, it is in horizontal position. That is, at D, it is equal to 800. At C, it is equal to 1300. At B is equal to totally 1600. At A is also 1600. So, take a suitable scale to represent this load and draw the diagram. That diagram is known as here shear force diagram. Okay, in this case, we can take 100 newtons is equal to 10 centimeters. That is 1 mm nothing but representing 10 newtons. Now, this is construct the diagram. Now, in second case, that is a bending moment diagram. The bending moment diagram is the negative for the cantilever beam because the effect of bending moment is having on the beam is hanging, hence it is a negative. Always remember the bending moment at free end is always 0. Hence, at D position, the bending moment is equal to 0 now. So, I can take it as now here M D is equal to 0 position now. Now, second, the bending moment at C is equal to, you can take it as MC. It is equal to 800 into 0.8 now. That is force into distance, which is equal to 800 is the force that in at C. That is the distance is equal to 0.8 is given. That is nothing but equal to 640 Newton meter now. Similarly, the bending moment at B is equal to, we can take it as a MB. That is at B, the bending moment created by the force at C, that is 500 newtons, as well as the at D, 800 newtons, we have to consider, which is equal to MB is equal to, we can take it as 500 into 0.7 plus 800 into 0.7, 0.8 is equal to 1.5 meters. So, this values we have to take 350 plus it is equal to 1200, which is equal to 1550. We have to take it now. Similarly, the bending moment at A is equal to the bending moment created by the 300, 500 and 800. We have to take it now. So, here now, the bending moment at A is equal to, I am taking M into A, which is equal to 800 is there now, 800 into total length of the beam is equal to 2. So, the bending moment created by the forces at A is equal to 800 into length of the beam is equal to 2 plus at 500 into 1.2 plus 300 into 0.5. But all this just treated as negative because the effect is hanging now. This value is equal to 2350 Newton meter now. So, first of all, while drawing bending moment diagram, draw horizontal lines, which is equal to the length of the beam as shown in figure. Draw the lines, vertical directions, which is passing through the point at which the load is acting like this. Right now, the bending moment at free end is equal to 0. At C already we calculated, which is equal to 640. So join these points by straight lines. Already I told for the point loads it should be joined by straight line because it is proportional to the distance only. At B is equal to, again join B and C, its value is equal to 1550. At A is equal to 2350. This should join the points now. Okay, this diagram is representing the bending moment diagram of the cantilever beam when it is subjected to 3 point loads B, C, D as shown in figure. Now we are considering shear force and bending moment diagram for the cantilever beam when it is subjected to uniformly distributed load over it now. Let the cantilever beam is AB as shown in figure, having length L is equal to L, carrying uniformly distributed load, generally it is called UDL, lowercase letter w per unit length. Now, the shear force at B is equal to, because it is uniformly distributed entire its length in such a way that its load is W per unit length now. So here at B, the length is equal to 0. So W into 0, because we are not the reference point, we are taking that free end. At this position, the shear force is equal to 0 now. Hence, in order to draw the shear force diagram as well as the bending moment diagram, first of all, draw the figure to represent the forces which are acting on it. From end position now, draw the lines as shown in figure, and we are considering one point X. Again, draw the vertical line as shown in figure. At convenient length, just draw a line AB to represent the shear force diagram of the given beam. Since the shear force is positive, hence it should be always above the reference lines AB as shown in figure now. At B, the shear force is equal to 0 now. Now, the shear force at a distance of X from the B is equal to W into X. That is the unbalanced force which is acting toward the right hand side of the beam now. So, which is equal to W into X now. That means it is a proportional to the distance. When the distance is increasing, the shear force is also increasing now. That is, it is nothing but treated as a following just line law now. Straight line law now. Hence, at a distance of X, draw a line vertical lines, which is equal to W into X. Because the shear force at this position is W into X. Okay, join the points by a straight line like this now. Similarly, the shear force at C is equal to, here now, here it is equal to, that is at C is equal to the total force. Total force is nothing but equal to how much it is now? W into L now. Here W into L. That is representing here now, W into L. That is unbalanced force. So W into L, you have to draw vertical lines. Join, that is here now, X point to straight lines. Or in other words, from B to C, draw lines, straight lines to meet the B point. This diagram is in the form of triangle. It is representing the shear force diagram for the beam when it is carrying uniformly distributed load. Now the bending moment diagram. The bending moment already told it is equal to 0 at the free end, whether it is a point load or uniformly distributed load acting on it. So here 0. At X is equal to, here the force into distance is required. The total force is acting, that is unbalanced force, is equal to W into X. Already we have taken now. Here between these points is equal to W into X. But where is acting now? The point of application of the force is required now. Hence it is acting in the middle now. That is at a distance of X by 2 now. That is the total load is equal to W X, but it is acting at the center now. that is center of gravity now of the beam now. So it is equal to how much it is distance here? X by 2 now. That is the bending moment at a point X from the B point is equal to W into X into X by 2 now. Or in other words, which is equal to W into X by 2 is equal to WX square. Here again it is a negative because of agging now. Similarly, the bending moment at a distance of L from B position now, that A is equal to, we can take it as, that means X is equal to L, which is equal to minus of WL square by 2 now. Since here the diagram is representing now, that is proportional to the square of the distance, because here at a distance of is equal to X is equal to how much it is? WX square by 2 now. That means it depends upon the square of the distance from the free end. Hence the curve is in the form of parabola as shown in figure now. This curve is called parabolic curve now. Okay, based on uniformly distributed load, we are taking one problem here. A cantilever beam of length 2 meters carrying uniformly distributed load of 1.5 kilonewton per meter run over the whole length and a point load of 20 kilonewtons at a distance of 0.5 from the free end as shown in figure. Draw the shear force and bend moment diagrams. Because the given data in the problem is the length of the beam. Length of the beam is equal to 2 meters now. The point load at B is equal to, here now, the point load at B here at a distance of 0.5 meters is equal to 2 kilonewtons. It is acting, and the remaining length is the uniformly distributed load. Now from the diagram now, in order to draw the shear force and bending moment diagram, just after drawing the beam as well as the representing the various forces acting on it, draw the vertical lines passing through the points at which the loads are acting, that is at B position, at C position, one more is the at A position drawing. At a convenient distance, draw horizontal line to represent the length of the beam in order to draw the shear force diagram now. The shear force at B is equal to 0. For the uniformly distributed load, shear force is equal to W into X. X is equal to 0. Hence at B is equal to, the shear force is equal to 0 now. Now, the shear force at C is equal to the unbalanced force which is acting toward the right hand side, which is equal to 1.5 kilonewton per meter. This is uniformly distributed load. This on an entire length of, that is 0.5 meters. That is total load is equal to 1.5 into 0.5 now. Hence which is equal to, here now, 0.2, that is 1.5 into 0.5. It is given now. Just to represent that length which is equal to 0.75 up to this position now. Since it is a proportion to the length of the beam, we can join the D at C by using the straight lines. But at D C position now, suddenly a 2 kilonewton force is acting. Hence, to represent the additional load of 2 kilonewtons, draw vertical lines from D position. That is, the total unbalanced force at C is equal to 2 kilonewtons plus 1.5 into 0.5, that is equal to 2.05 now. Now the shear force at A position, that is unbalanced force, that is total force on the beam towards the right hand side is equal to 1.5 into, that is 2 meters. That is 1.5 into 2 means nothing but it is equal to 3 kilonewtons plus 2 kilonewtons already there now, total 5. So represent 5 according to the scale. Just draw a line vertically upward direction. So that AF is representing the shear force at a point A position now. Okay, join these 2 points by straight lines. This diagram is representing the shear force diagram for the cantilever beam when it is subjected to uniformly distributed load as well as the point load at C position. For the bending moment diagram, draw lines to represent the length of the beam as shown in figure. Since the bending moment diagram is the negative for the cantilever beam because of hanging effect, so first we have to represent the bending moment values at various sections, that is at B, C as well as the A in a figure. The bending moment at B, that is the free end, is always equal to 0. At B is always equal to 0. And at C position now, the bending moment is equal to, at C, that is load multiplied by the distance. The load which is equal to between B and C is equal to, we can take it as 1.5 into 0.5. This is the load, the bending moment at a distance of C, that is 1.5 into 0.5. But it is acting in the middle because it is uniformly distributed load. We can take it as 0.5 2 now. That is the W into X by 2 now. Since it's a negative hanging effect, just you have to take it as a negative now. So represent this point, the values is equal to 0.1875. Okay, represent the vertical lines to represent this load, but join B and C points by using parabolic curve now, because the bending moment is depending on square of the distance between the points now. Now at A position now, the bending moment at a point A, that is M into A, is equal to the total load, that is unbalanced force, that is uniformly distributed, is equal to 1.5 into 2. But where it is acting now, the load is acting in the middle. We can take it as 2 by 2 plus the point load is also acting now. The point load is 2 into 1.5. It is totally nothing but in negative values now. So this values is equal to minus 6.20 now. So from this line, first of all, draw the lines to represent the length of the beam. At B is equal to 0. At C is equal to, already we determined 0.18. Just join these points by using parabolic curve. At C, nothing but 6. Join A and C again by using parabolic curve. This curve is representing shear force diagram or the distribution of bending moment, this entire length of the beam now. Now shear force and bending moment diagram for the combination of uniformly distributed load and point load. One more problem. A cantilever beam of 1.5 meters span is loaded as shown in figure 6a. Draw the shear force and bending moment diagrams. The given data in the problem is the length of the span is equal to 1.5 meters. The point load at B, it is equal to 2 kilonewtons. 2 kilonewtons. Uniformly distributed load is equal to 1 kilonewton per meter. From C position to A position is given. Here it is equal to 1 kilonewton per meter now. The length of the cantilever AC, the distance between AC is equal to 1 meter now. Now first we will draw the shear force diagram now. So after drawing the cantilever beam and also representing its forces, draw the lines, vertical lines, downward directions, just passing through the various points at which the forces are acting, like this. And at your convenient distance, draw lines, horizontal line to represent the length of the beam as an ordinate to represent the shear force diagram. The shear force diagram is a positive, hence just maintain sufficient gap between the cantilever beam as well as the ordinate of the shear force. Now at B, the shear force is equal to 2 kilonewtons. draw vertical lines such that here 1 kilonewton is equal to 10 mm, the 20 mm draw vertical lines. It is remains constant up to here C position now. That is we got the shear force at B is equal to, we are saying this FB, which is equal to 2 kilonewtons. Shear force at C is equal to, again, the unbalanced force 2 kilonewton only. The shear force at A is equal to, FA is equal to, you can take it as a unbalanced force means 2 kilonewtons and the load which is acting between A and C now. That is 2 plus 1 into 1.1 into total length is given 1.5. That the remaining is only 2 plus 1 into 1 kilonewtons. This length is equal to, the distance between these two is equal to again 1 now. So which is equal to 2 plus 1 is equal to 3 now. So draw the vertical lines to represent here 3 now. You can join these points like this. This diagram is known as the shear force diagram for the beam now. And in order to draw the bending moment diagram. Here draw the horizontal lines. Just here, these are the forces are acting. There, the bending moment at B is equal to 0. Free hand is already completed. At C is equal to, the bending moment at C is equal to force into distance, that 2 kilonewtons multiplied by 1.5. That is 2 into 0.5. It is equal to 1 kilonewtons. Just represent 1. Since it is depends upon the distance only, you have to join these points by using the straight lines now. Now the bending moment at A is equal to, first of all we are considering the effect of point load, that is 2 into 1.5. 2 into the distance between these points is equal to 1.5. It is a negative. And again, the effect of uniformly distributed load required, that is 1 into again 1 by 2 now. That is 1 is nothing but the load W into L and L by 2 now, which is equal to, here it is equal to 3, here minus 0.5, total is equal to minus half 3.5 kilonewton meter now. So represent just here now 3.5 kilometer downward directions. Since uniformly distributed load is there now, the bending moment is proportional to the square of the distance is there, because the W into X by 2 we are taking now. Here W into X by 2. That is depends upon square of the distance. Hence it follow the parabola, or this curve is known as the parabolic curve. Hence you join these points, these 2 points, that is A and C, by using parabolic curve. A cantilever beam of AB 2 meters long carries uniformly distributed load of 1.5 kilonewton meter over a length of 1.6 meters from the free end. Draw the shear force and bending moment diagram for the beam now. Here the given data is a cantilever beam of AB 2 meters long, that is length of the beam is equal to 2 meters. Uniformly distributed load of 1.5 kilonewtons over a length of 1.6 meters. That is UDL is equal to 1.5 kilonewtons and the carrying length is equal to 1.6 now. Okay, in this one the given data is the shear force here represented here now. This is the diagram is given. Now after representing the forces which are acting on the beam, Draw lines which are passing through point B, where this end B is represented. One more is the end A. At a convenient length, draw lines to represent the ordinate or length of the beam for drawing shear force diagram. The shear force at B is equal to 0 because the uniformly distributed load, it is there. With respect to the W, that is B, the shear force is equal to W into X. It is X is equal to 0 because the reference point is B only, and here it is 0 now. At C there now, the shear force is equal to how much it is? 1.6 into this distance is given how much it is here now, over length of 1.6 is given. W is equal to 1.5. That is 1.5 into 1.6, which is equal to 2.4 now. That is up to this 2.4 you take and draw the lines. This is nothing but representing 2.4 load now. That is 1.5 multiplied by the 1.6 now. So, join these points by straight lines because the shear force is now following the straight line law now. That it depends upon the length of the beam. But between A and C, the unbalanced forces remains constant. Hence, draw A horizontal lines to meet the vertical line which is passing through point A now. This diagram is known as shear force diagram for the cantilever beam, which is a positive now. The second one, bending moment diagram. The bending moment at B is equal to 0. The bending moment at C is equal to W into X by 2 required. At C is equal to W is equal to point, that is uniformly distributed, which is equal to 1.5. Distance is given 1.6 by 2 values, which is equal to now here, which is equal to 1.2 minus of 1.92 now. Now the bending moment here is given. Here draw the lines which are passing through point A, C, B. Here it is equal to 0 at B position. At C position, it is equal to 1.2. Just join these points again by using parabolic curve now. At A position now, that is bending moment at A is equal to dA is equal to the force into distance is required. That is at A is equal to the total force is equal to how much it is here now, 1.5 into 1.6. This is the total load, that is W into length is required now. Where it is acting now? It is just in the middle of AC now. Somewhere the load is acting at this position. That is the distance is equal to 0.8 now. The remaining length is equal to here, it is equal to 0.4 now. This distance. Total length is equal to 0.4 plus 0.8, which is equal to here now 1.2. You can take it as 1.2. Or in another words, which is equal to, we can take it as 0.4 plus 1.6 by 2 now. So from this relationship we got to, which is equal to minus of 2.88 kilonewton meter now. So just to take this values. Join these points again by using the parabolic curve. This curve is known as a shear force diagram. Now, in another problem, a cantilever length of 1.5 meters is loaded with UDL of 2.5 kilonewton per meter, run over length of 1.25 meters from the free end. It also carries a point load of 3 kilonewtons at a distance of 0.25 from the free end. Draw the shear force and bending moment diagram for the cantilever. Given data in the problem is the length of the span is given, that is AB is equal to 1.5 meters. The point load at B here nothing but here the point load at C is equal to, that is 3 kilonewtons, which is acting at a distance of 0.25 from the B end position. That is at C is equal to 3 kilonewtons acting now. Uniformly distributed load is carrying between B and D now. This length is equal to here now 1 meter plus 0.25, that is 1.25 meters now. Yes, given now. First of all, we have to draw the shear force diagram now. The shear force diagram, not draw the shear force diagram. First of all, draw the cantilever beam and represent all the forces which are acting on it as shown in figure. From the point B, draw a line vertical and downward directions. C, one more lines. At D, one more lines. At A, one more line as shown in figure now. After that, draw a line AB to represent the length of the beam as an ordinate for drawing the shear force diagram. The shear force at B is equal to 0 because it is subjected to uniformly distributed load between B and D. At B also is driving only uniformly distributed. Hence, at B is equal to W into X. X is equal to 0 because we are following just a reference point as B point only. At C position now, the unbalanced force which is acting between B and C is equal to 0.25 length. Load is acting 2 kilonewtons per meter. That is 2 into 0.25. Here this values is given 0.5. It is representing up to according to the scale now. Okay, join these points by using straight lines now. Because it depends upon the distance between the points only now. At C position now, 3 kilonewtons force is acting there. And so suddenly the load is increases upward directions. The total load now becomes 3 plus 0.5, 3.5 now. Now at C position now, D position here now, the total load is equal to, which is acting toward the right hand side is equal to, that is 2 kilonewtons per meter. The length is equal to 1.25 is acting. Again 1.2 is also acting, this is 3, which is here equal to 2.5 plus 3, which is equal to 5.5. It is acting at this position now. So join the points by straight lines now, straight line law now. Here between A and D, since there is no force acting, hence the shear force is a constant, hence join horizontal lines like this. Hence this diagram is known as shear force diagram when it is subjected to point load as well as the uniformly distributed load. Bending moment diagram. The bending moment diagram for the cantilever beam is negative because having hanging effect. Here draw the lines as usual, passing through the various points, vertical lines as shown in figure. Here AB is representing length of the beam. The bending moment at B is equal to 0 because of free end. At C is equal to M into MC is equal to, here the bending moment at a point C is equal to load into X by 2 required, where X is nothing but the distance between the points that is required. So here according to this problem now, W is equal to 2 kilonewtons, X is equal to 0.25, that is 2 into 0.25 into 0.25 divided by 2 now. This is equal to 0.0625. It is given negative because of hanging effect now. Since the distance here depends upon the square of the distance, here represent 0.625 according to the scale, draw vertical and downward directions and join the points by using parabolic curve now. And the bending moment at D position now, here MD, it is equal to the effect of uniformly distributed load is equal to 2 is the load into X. X is equal to how much? 1 into 1 plus 0.25, that is 1.25. It is acting at 1.25 by 2. Again, that point load is also there now, 3 kilonewtons. That is 3 into here 1. This entire thing is negative because of hanging effect now. So this value is equal to, it is equal to 1.2563 kilonewton meter now. Now similarly, the bending moment of point at A is equal to, we have to consider the effect of point load as well as the uniformly distributed load which is acting between the points B and D now, which is equal to L W, that is load is equal to 2, length is equal to 1.25, it is there, distance is equal to here, it is acting in the middle, that is 1.25 by 2, but we are considering at a point 2, hence 1.25 by 2 plus 0.25 we have to consider, minus point load is equal to 3 into 1 meter plus 0.5, 1.25 now. So on doing calculations, the value is equal to minus of 5.9375 kilonewton meter. So you have to take the distance as a here vertical line. Just join all the points by a curve, parabolic curve. This diagram is representing the distribution of bending moment is over the entire span. A cantilever beam of length of 5 meters is loaded as shown in figure. Draw the shear force and the bending moment diagram. Here, the forces which are acting on cantilever beam are shown in figure. Here, AB is representing the length of the beam, which is equal to 5 meters. At B, a point load of 2.5 kilonewton is acting. At C and D, it is having uniformly distributed load up to D position, but E point 3 kilonewton point load is acting now. That is the 2 point loads as well as the uniformly distributed load acting over the beam. So first of all, we have to draw the shear force diagram. So after drawing the cantilever beam and representing its forces which are acting on it, draw the vertical lines passing through the various points B, C, here D, E, as well as A as shown in figure, and draw a line, horizontal line, which is representing the length of the beam as shown in figure now as the ordinate. Now the shear force at B is equal to, that is unbalanced vertical force, which is equal to 2.5 kilonewtons. Just represent as per the scales. Assume 1 kilonewton is equal to 10 mm now. That's 2.5 centimeters. You have to keep vertical line. Up to C is the constant. Draw the horizontal line as shown in figure. At D point, the total unbalanced force is equal to 2.5 kilonewtons already acting this point load plus 1.1 kilonewton for the length of 2 meters. The total load is equal to 1 into 2. That is total is equal to 3. That is here it is equal to 2 into 1 here plus 2.5 it is acting. Total 4.5. Just to take 4.5 and join the points by using the straight lines now. Since uniformly distributed load is acting on it, it will follow the straight line law now. There is no load acting between D and E, hence join the points D and E by using horizontal lines now. At E position now, additionally 3 kilonewtons is acting. That is 4.5 plus 3, that's 7.5 length. Again increasing its length now. And draw horizontal lines to meet the vertical lines passing through a point A as shown in figure. This diagram is representing the shear force diagram for the cantilever beam when it is subjected to 2 point loads as well as the one uniformly distributed load. Now bending moment diagrams. The bending moment diagram set B is equal to 0 because it is a free end. At B it is equal to 0 as shown in figure. The second one is the bending moment diagram set to bending moment at C is equal to force into distance, that 2.5 into 0.5, which is equal to 1.25. Since it is only depending on the length of the distance between the B and C, hence it follows the straight line law. Between B and C, uniformly distributed load is acting. So the bending moment at a point D is equal to, we have to consider the effect of point load as well as the uniformly distributed load, which is equal to 2.5, that point load. The distance is equal to 0.5 into 2, that is nothing but equal to 2.5. Here it is there, plus the effect of uniformly distributed load. The total uniformly distributed load is equal to 1 into 2 now, the 1 into 2, but it is acting at a distance of 1 by 2. So here we can take it as 1 into 2 into 2 by 2, W into X by 2 now. So from this relation we got it is equal to 8.25 kilonewton meter now. The bending moment at E is equal to 2.5. The total distance between E and D is equal to 4 now. So 2.5 into 4, 1.5, 2 plus 0.5, it is equal to 4. Over. Again, the effect of uniformly distributed load, it is equal to 1 into 2, but it is acting in the middle now. Middle nothing but it is a 1 meter, again 1.5. So the total now becomes 2.5 now. So we can take it as 1 into 2 into 1.5 plus 2 by 2, just half of the length. So which is equal to 15 kilonewton meter now. The bending moment at A is equal to the end position now. We have to consider the effect of point load at B, uniformly distributed load, and point load at E position also now, which is equal to 2.5 into, that is regarding point load, 2.5 into length of the beam, it is equal to 5. It is there. And the effect of uniformly distributed load, which is equal to 1 into 2 now. So from this relation we have to take it now. The load is acting. Here 1 into 2 into 2 by 2 plus 2.5 plus the point load of this one is equal to 3 into 1 meter. From this relation we got 12.5 plus 7 plus 3. It is equal to 22.5 negative because of hugging effect. So you have to represent the points here D, E point and A point. Join these points just by using here uniformly distributed load there parabolic curve. You have to join it now. Okay, these are the problems we have taken for giving explanation the effect of uniformly distributed load, point load, and a combination of point loads as well as the uniformly distributed load acting on cantilever beam, and what are the shear force as well as the bending moment created on the beam we calculated. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.